Hello everyone, welcome to this presentation of a work for the International Conference on Cyberworlds 2020 to be held in Cannes the 28th September, 1st October 2020. My name is Andres Iglesias. I'm going to present this work entitled Swarm Intelligence for Automatic Color and Contrast Retrieval of Digital Images of Paintings. I belong to the University of Cantabria in Santander, Spain, and also Tohoku University in Funabashi, Japan. This work has been done in collaboration with my colleagues, Akemi Galvez from the same institutions, Eneko Saba from Tecnalia in Spain, Iztok Fister and Iztok Fister Jr. from the University of Maribor in Slovenia, and Javier del Ser from Tecnalia and also from the University of Basque Country, also in Spain. Well, this is the outline of my talk. First of all, I will start with the motivation of this work. Then I will describe a little bit about the problem to be addressed here. Then I will explain a little bit about a cuckoo search algorithm, which is the technique used here to solve the problem. Then I will explain the experiments and results we get, then the conclusions, and finally some acknowledgements. Regarding the motivation of this work, if you think about the current technology, we have a large collection of digital images of famous paintings available on the internet with just a few clicks. Just surfing on the web, you can find a lot of them, but most of those copies are affected by changes in color, contrast, and other visual artifacts that prevents art lovers and general fans to enjoy the real painting as it was originally created. So in this problem, we try to address this problem. Suppose they are giving an initial digital image. We call that a reference image. For instance, this one here, displayed here. Actually, this is a very famous painting. The name of this painting is Starry Night, and it was painted by a famous Dutch painter, Vincent van Gogh, in 1889. It's a famous oil painting, and is one of Van Gogh's finest works, but also one of the most iconic and recognized paintings in the history of Western culture. As you can see here, it shows a very rich color map with a prevalence of bluish tones. The relative percentage of the red, green, and blue channels is about 27, 33, and 39% respectively. But this painting is also interesting because it's a very good representative work of a painting technique called impasto, which refers to use of thickly textured and diluted paint that looks almost three-dimensional when painted on the canvas. A distinctive feature of this impasto technique are the visible brush strokes in the finished painting that, when dry, provide texture. The paint is seen sticking out from the canvas in globs when viewed from the side, as if it was coming out of the canvas, creating a kind of a, let's say, three-dimensional texture. As a result, the appearance of the painting is greatly affected by the illumination in the exhibition room, because this three-dimensional texture makes the incident line to be reflected, so shadows are created. In this case, Van Gogh used this technique to convey higher emotion and dynamism, as for instance in this movement here of the swirling clouds, which gives the viewers, at least for me personally, the feeling that the sky is moving and there is a lot of motion in this picture. This is one of the reasons we chose this image as a benchmark for this work. Okay, well. Once you have this image, suppose you are given a variation of this reference image generated by changing the color map and possibly other visual attributes in an unknown way. And for instance, you get this image here in this slide. Well, you can recognize it's the same painting, but actually it's quite different. According to our error metric, this painting, the similarity between this painting and the original one is less than 3%. Okay? So the goal here in this work is to compute optimal parametric values for some of such visual attributes, such that when we apply this parameters to the variation image, we obtain an image very similar to the reference one, according to our metric. Okay? So in this work, we focus on two visual attributes, color and contrast. The color represented as classically as triples in the RGB color model, normalized on the interval 0, 1, and then we consider the root mean square contrast given by this equation, where m and n represent the size of the in pixels of the image. Okay, so if we have R to be the reference image of size m times n with a contrast parameter c, and we get V, a variation obtained from R by a node modification of the color and contrast, our goal is to determine optimal values of color and contrast such that when applied to V, the resulting image V prime is similar to the original image according to a given matrix. Okay, given by this equation here, where here these values delta prime means the RGB components of the original reference image and the reconstructed image, R and V prime respectively, and C prime denotes the contrast of the original image and the reconstructed image. Well, this problem can be interpreted as, okay, be formalized as an optimization problem, which is very hard to solve actually, because it's continuous, it's overdetermined, is nonlinear, and is multivariate. So the challenge here is how to solve this very hard optimization problem. And the method we propose in this work is the cuckoo search algorithm. It's a method designed by Professor Xinse Yang and Xu Deb in 2010, and it's a powerful nature-inspired population-based meta-heuristic method for global optimization, which is inspired by the broad parasitisms of some cuckoo species that lay their eggs in the nest of horse birds of other species to escape from parental misbehaving, rising day or spring. So this behavior, this natural behavior, is used as a metaphor for this optimization problem according to these rules. I have no time to discuss this method in detail, but you can find the details in our paper, in the proceedings. So basically what we get is an algorithm like this, and we apply this algorithm to solve the problem with an initial population of individuals. Each individual is described by the RGB code of the image and this parameter, mu kappa, accounting for the contrast. Okay, so we start in this method with an initial population of randomly generated images, which are the individuals, and then the basic idea, kind of a genetic algorithm, if you like, is to evolve the system according to our metric to produce in new generations better individuals according to our fitness function, so that the process eventually converges to a very good solution. Okay, so it's a competitive system where the best individuals are transferred to the next generation. The number of generations of iterations we use in this paper is 10,000, with a initial population size of 50 individuals and a replacement probability for the method of 0.01. Okay, going to the details of our experiments and results, taking the initial image I showed in the previous slide, and taking different variations of that images generated randomly with an initial population of 50 individuals, taken from the initial picture. By changing randomly the color map and contrast, we generate a large collection of individuals. Here I show only 10 of them. You can see the details about the algorithm in our conference paper. Then, evolving the algorithm, what we get is basically a collection of images over the generations, and then we select the best of them, which is shown here. Okay, so this is the global best at that particular generation, from generation 0 to generation 9,000, with the step size 1,000. Okay, so as you can see, the method is improving over the time. At the beginning, not that much. Okay, even the color map and the contrast are quite different from each other, But eventually, at the later stages of the method is improving and is getting closer and closer to the reference image. We can see this effect in the similarity error value in this table, showing the similarity error value according to our metric from generation 0 to generation 10,000 with a step size 500. This table is also displayed, is also included in the paper in the proceedings. So just to close with the conclusions of this work, as you can see probably from the numerical values here, okay, at the final numerical value, you can see here at the beginning the similarity error is more than 97%, so it's a huge error, but the error is decreasing over the duration, as you can see here in these columns, and at the end the error is more or less about 5.7%, so which is a very good reconstruction value. So the method performs pretty well, and you can see here in the image that the final image is quite close to the original one, to the reference one, which is displayed here. Okay. So the conclusion is that the method performs pretty well. It's able to replicate the reference image with high accuracy, visual accuracy, and also numerically. Of course, it can be still improved, and we are working on that as our future work. But we are confident that this method is promising and opens the door for future research in the world with hopefully very good results. And the applications arise in image cleaning and restoration of digital images, in image and painting, and many other fields. Regarding the limitations of this work, the main problem is that the CPU time is still a challenge. I mean, the method takes time, particularly because we are working with images, so we generate a large collection of images, and this method therefore takes a lot of time. And this work only considers two visual attributes, the color and contrast. We would like to include other visual attributes in our future work in the field in coming papers. So this finishes our presentation. Thank you very much for your attention. If you have any question or comments, we are glad to contact you. So please drop us an email and we'll contact you. We'll be glad to be in touch with you. Finally, some acknowledgements. This work has been done with the financial support of some funding research agencies from the Spanish government, the Ministry of Science, Innovation and Universities, the Society Soderkamp, the Regional Society for Regional Development in Cantabria, also the Basque government about two different projects, MITEC and Ecatec, the Slovenian Research Agency, and the European Commission, particularly for the Maria Skłodowska-Curie actions from the PDE Year European project. Thank you very much to all of them, and thank you very much to you for your interest in this talk.